Unlock the potential of artificial intelligence. Welcome to Deep Learning and Generative AI.
This is part 2 of our lecture on recurrent neural networks. We now explore modern gated architectures designed to address gradient instability and long-term dependency modeling. All right, so here's our game plan. First, we're going to dig into why simple RNNs have such a hard time with memory. Then we'll look at 2 brilliant solutions, the famous LSTM cell and its more streamlined cousin, the GRU. After that, we'll see how these building blocks are used to create some really advanced models. And finally, we'll put them all side by side to see the pros and cons and uncover their ultimate limitations. Okay, so before we can really appreciate these newer, fancier models, we've got to understand what they're fixing. Why exactly do the vanilla RNNs that we talked about in part 1 just fall apart when they have to remember things for a long time? The problem, it turns out, is baked right into their core mathematics. And this right here is the smoking gun. Remember backpropagation through time? Well, to update the weights based on an error far back in the sequence, the gradient signal has to travel backward through every single time step. Each step involves multiplication by the same recurrent weight matrix. Now, if the values in that matrix are, on average, less than 1, what happens when you multiply a number by something less than 1 over and over and over again? It shrinks exponentially. The signal just vanishes into nothing. By the time the error signal from time step 100 gets back to time step 1, there's basically nothing left to learn from. So let's just formally define that. We call it the vanishing gradient problem. The error signals that are meant to guide learning become so tiny, they're effectively zero. This means the network becomes incapable of connecting events that are far apart. It can't learn that the word "it" at the end of a long paragraph refers to the cat mentioned way back at the beginning. It's like the network has severe short-term memory loss, and that's the fundamental hurdle we need to get over. I love this analogy because it's spot on. A vanilla RNN is a leaky bucket. You pour new information in, but the old information is constantly being overwritten and leaking out. The solution? We need to stop overwriting everything and start controlling the flow of information. We need to build a safe, not a bucket. This is where gates come in. Think of a gate as a tiny neural network with a sigmoid activation. It outputs a number between 0 and 1. A 0 means gate closed, nothing gets through, and a 1 means gate open, let it flow. This gives the network a way to learn what to keep and what to throw away. And that brings us to our first major implementation of this idea, the long short-term memory cell, or LSTM. This was a groundbreaking architecture that really cracked the code on building a robust memory system for neural networks. Okay, I know this diagram looks a little busy, but the core idea is incredibly elegant. The LSTM introduces 2 separate pathways for information. You have the hidden state, HT, which is kind of like the network's short-term working memory. But the real star of the show is this new thing called the cell state, CT. Think of the cell state as a protected memory superhighway, and its traffic is carefully controlled by 3 gatekeepers, a forget gate, an input gate, and an output gate. And this separation is absolutely crucial. The cell state is the express lane. Information can travel along it for many, many time steps without getting mingled by a bunch of matrix multiplications. This is what preserves the long-term memories. The hidden state, on the other hand, is more like the local access road. It's what the network uses to do its work and make a prediction at this specific moment in time. So let's look at the first 2 gatekeepers. First up is the forget gate. It looks at the new input and the previous hidden state and decides, for every piece of information in the old cell state, should we keep this or forget it? A value close to 1 means keep it. A value close to 0 means forget it. At the same time, the input gate is looking at the new information and deciding which parts are important enough to even be considered for storage in our long-term memory. Now this is the secret sauce. This is the whole reason LSTMs work so well. Look at how the new cell state, CT, is created. We take the old state and multiply it by the forget gate's decision, and then we add the new information from the input gate. That plus sign is the most important part of this whole diagram. Because we are adding, not multiplying, the gradient can flow backwards through this addition operation almost perfectly unchanged. This creates that uninterrupted superhighway for the error signal, effectively solving the vanishing gradient problem. And this beautiful mechanism actually has a name, the constant error carousel. It's a perfect description, right? It's like the error signal just hops onto this carousel and can ride it backwards through time without getting weaker, allowing the network to connect cause and effect across huge distances in the sequence. All right, last piece of the puzzle, the output gate. So we've updated our pristine long-term memory in the cell state. Now the output gate's job is to look at that cell state and decide which parts of it are actually useful for the task at hand right now. It filters the cell state to produce the new hidden state, HT. And that hidden state serves two purposes. It's the final output for this time step, and it's the short-term context that gets fed into the next LSTM cell. Now, LSTMs are amazing, but they have a lot of moving parts. 3 gates, 2 separate states. They can be computationally heavy. This inspired researchers to ask, can we get the same benefits with a simpler design? And the answer was the Gated Recurrent Unit, or GRU. This comparison shows you everything you need to know. The GRU is all about simplification. First, it gets rid of the separate cell state and just has one unified hidden state, HT. Second, it combines the forget and input gates into a single update gate. The result? Fewer parameters, which means it often trains faster and can sometimes perform just as well as, if not better than, an LSTM on certain tasks. The elegance of the GRU really shines in its math. That update gate, ZT, basically controls a trade-off. It decides how much of the old hidden state we should just carry over and how much of the new proposed information we should mix in. It's a direct interpolation. If ZT is close to 1, we mostly keep the old memory. If it's close to 0, we mostly use the new stuff. It's a much more direct way of balancing past and present. And the reset gate helps decide how much the past should influence that new candidate information in the first place. Okay, so now we have these incredible building blocks, LSTMs and GRUs, that can actually remember things. So what can we build with them? Well, now we can start constructing much more sophisticated and powerful architectures for handling sequences. One obvious move is to go deep. We can stack these RNN layers on top of each other. The first layer might process the raw words, the second layer takes the output of the first and might learn about phrases and grammar, and a third layer could learn about the overall sentiment. Each layer learns progressively more abstract, higher-level features from the sequence. Another really powerful trick is the bidirectional RNN. Think about it. When you read a sentence, you don't just use the words that came before, you also use the words that come after to understand the meaning. A standard RNN can't do that. A bidirectional one can. It runs one RNN forwards through the sequence and a completely separate one backwards. Then, at every word, it just glues their two hidden states together. This gives the model a super rich understanding of the context from both the past and the future. And that brings us to what was, for a long time, the dominant architecture for things like machine translation, the encoder-decoder model. It's beautiful. You have 2 RNNs. The first one, the encoder, reads an entire sentence, say in German, and its only job is to squish down the meaning of that whole sentence into a single vector of numbers. We call this the context vector. Then, the second RNN, the decoder, takes that single vector and uses it as a starting point to generate the English translation, one word at a time. But, as powerful as this is, it raises a pretty serious question. Can you really expect one single fixed-size vector to perfectly capture every single detail of a really long, complex sentence, let alone an entire paragraph? It seems like a lot to ask. This single vector becomes an information bottleneck. The longer the input, the harder it is for the encoder to cram everything in, and important details are bound to get lost. So let's pull all these threads together. We're going to do a direct comparison of the models we've seen. And we'll use that idea of the information bottleneck to really understand the fundamental limits of this whole recurrent approach. This table gives us a great summary. The vanilla RNN is simple and fast, but its poor gradient stability makes it useless for anything but short sequences. The LSTM is the king of long-term memory, thanks to that protected cell state, but it pays for it with a higher parameter count and slower computation. The GRU, then, is the happy medium. It offers robust gradient stability, just like the LSTM, but with a more efficient, streamlined design. In practice, the GRU is often a fantastic starting point for many problems. And this brings us right to the edge of the next big revolution in deep learning. That information bottleneck in the encoder-decoder model is a real problem. The decoder only gets one summary of the entire input. But what if we could do better? What if, at every step of generating a translation, the decoder could look back at the entire input sentence and pay attention to the specific words that are most relevant for predicting the next word? Recurrent networks introduce powerful inductive biases for sequential data. However, their computational limitations ultimately motivated attention-based models, which we will study next.